Impressionist. So, whoops. So this course, the title of the class is called Impressionist Geometry. And just like Impressionist painting, the prerequisites of this course is that you know all the material that I will be explaining in a clear way. And that will give you a different perspective. Okay? If not, you still get some impressions, so that's not a problem. Okay? All right. So so what do we study in geometry? Okay. And some of the central questions we study in geometry. First, of course, it's a classification of all the spaces, and there could be different type of spaces, whether you are a topological space, algebraic space, or something. Okay? And for different classes of spaces, the classification could be a very rough classification or very precise classification. So it depends on the setting. Okay? And I will explain talk a little bit more about that today, but it's not the main concern of this particular lecture series. Okay? So we'll talk a little bit, but we're not going to be doing too much of the classifications. The second is that once you're given a particular space with some geometric structure, you understand that specific geometry. So most of the situation, the thing that you're trying to understand is that inside the space you have some cycles. So it could be some submanifold, vector bundles, things like that. And then we want to understand how they interact with each other. Those are called the intersection theory. Of cycles. Okay. And the next questions would be duality between very different behavior of geometry that turn out to be equivalent in a very subtle way. So these are the topics we will discuss more. So let me say a few words about here and then come back to the first problem. So just say a few comments, some remarks. On 2. Okay. So intersection of cycle, the thing that we traditionally study at the very beginning is the plane geometry. This is where geometry begins, basically. For example, if you draw any free line, and then you bisect the line, bisect the angle, and then they intersect at the point, things like that. It's a very typical, very classical basic geometry questions. Okay? And more sophisticated so this is an example of what we mean by intersection theory of cycles. In this case, the cycle is just a straight line in plane geometry. Or more generally, you can look at some curved subspaces. So this could be, more generally, is the derived category of coherent shift of algebraic variety. Okay. And that is even still a very active research area, lots of interesting problem here. And another one is the Foucault category of Lagrangian, of a symplectic manifold. And those have been developed in the last 20 years and lots of study. Okay. And there are more, but there are things which are more common. And for the duality, and the simplest one would be if you have a space, and then you have a dual space. And then you have a subspace here, and then you have the corresponding dual spaces, which are things which are perpendicular to that. And then you maybe have a lattice, and then you have a dual lattice, and so on. So these are classical linear duality. And you can do a projective versions called projective duality inside linear space, inside projective spaces. And in algebraic geometry, for example, like Brooker formula, study the degree of a dual curve or something like that. And then you also have a modern version related to our category. It's called homological projective duality. And these are wise generalization for homological of this type linear duality categorically. And also you have like mirror symmetry relating these two types of sub-objects. And you also have like a 3D mirror symmetry. That was from Friday. So you have 2D, 3D mirror symmetry. Okay. Or more generally, and also you also have a LEUNG duality or S duality. And so on. Okay. So these are some examples of in various degrees. All right. Now I come back to say a few words about the classifications of spaces. Classifications of spaces. I'll explain more about what type of spaces right after this. So the first cases is like a topological spaces or smooth spaces. And those are called manifolds. So in this case, okay. So they usually classify according to dimensions. So one dimension. So for simplicity, we'll just look at space which are connected and which are oriented and compact, things like that. Okay? There are variation, but for today, it's easier to just present it this way. So in one dimension, the only space, doesn't matter whether you are smooth or topological, it's just a circle, that's it. Very simple. In 2 dimensions, and then you have a S2, you have an elliptic curve, and then so on. And then so you know all of them by looking at the number of holes. The number of holes completely determine the possible spaces. Okay, it doesn't matter whether it's smooth or topological. So these are very classical, simple statements. And things become hugely more complicated when you go to dimension 3. And the classifications is known, is usually called the first geometrization conjecture, and is proved by Pellemers and Hamilton. So it's proved by Pellemers, and with earlier work by Hamilton. So it's like this, that in this case, you basically has three types of spaces. Say more, in what sense, three different types of spaces. They are elliptic type, parabolic, and hyperbolic type. Okay, and in 3 dimensions, it turns out there are 8 of them. Okay, so these are basically, in all these cases, the universal cover of this is constant curvature 1, 0, and -1. Okay, and then in 3 dimensions, the 8 of such geometry is homogeneous geometry. So in a way, so up to some, so this classification up to a discrete quotient. Okay, so in this case, it's very complete classification. Okay? And it's and the proof is hugely complicated. And to comment about the proof is in the proof. First of all, it's a topological statement, but the only proof is through geometric analysis. By studying rigid flow. So that was the original Hamilton's approach. So you have to introduce auxiliary data to help you to find a good metric, so-called canonical metric. And another comment is, even though we are trying to find a classification of a smooth space, inevitably, you have to understand what happened in the singular case. Okay, so you need to study singular. You need to include the study of certain singular spaces, inevitably. So this is some of the things we always learn, that even the main interest that we are only a smooth manifold. To understand smooth manifold, you have to allow possible singular spaces. In 4 dimensions. Now so first of all, this proof originally people are always first study the Poincare conjecture, which is in the case with it simply connected. Then the only space has to be S3 to do classical Poincare conjecture. Okay. Now in dimension 4, there's a difference between smooth and topological case. And first of all, we first of all have to restrict to the assumptions that pi1 is small, let's say 0. Okay. And the reason is if you allow all possible fundamental group, that is not a classifiable question, because every finitely presentable group is the fundamental group of a 4 manifold. And that finite presentable group is an unclassifiable question. Okay? So therefore, to do that, we do that. We restrict to a simply connected case, and or find a small fundamental group. Okay. So in the topological setting, this is solved by Friedman. Okay. In the topological fundamental. Yes. In the topological case. Yeah. And that work in a smooth case, but not a classification, is some constraint of what possible type. Those are by Donaldson's theorem. Okay. And there are lots of work in dimension bigger than 5. Again, these are topological case, simply connected. Topological case. And dimension in topology, which is very different from algebraic geometry analysis, the bigger the dimension, the easier the problem is. Okay, so this has been hugely successful, like a work by John Miller to find counterexample to Poincare conjecture, and Smell to prove a version of that Poincare conjecture, H coordinate field, and so on. So there are lots of early study in topology, okay, and so on. Now, let's say if the manifold, instead of defined by holomorphic, locally controlled by holomorphic smooth function, maybe now defined by holomorphic functions. Okay? Those are complex manifolds. Okay? So in dimension 1, now because it's a complex dimension 1, if you look at it as a real manifold, there are already 2 dimensions. Okay, and so all this will be one-dimensional complex manifold. Okay, and so each of these, let's just call it sigma G. Okay, will emit a complex structure. In fact, there are many complex structures. In fact, the number of complex structure, all the possible complex structure, they form a space of dimension 3G minus 3, and that space has a lot of good structures. Okay, and so there are either a Teichmüller theory or the moduli problem, depending on whether you fix a marking or not. Okay, so these are like a Teichmüller theory. Or Mumford's moduli theory. Okay, depending on the setting. So there has been lots of study about the geometry of this space of all possible complex structure on that. In dimension 2, immediately the problem is a lot more complicated, and that is a famous work by Cordeiro, classification of complex surfaces. So again, the classification are divided into like these 3 different types, or maybe in terms of so-called Cordeiro dimension now. Okay, and so these are the analog to the high genus ones. These are called the general type. Then that problem is related to so-called geography. Okay, meaning that such space has a lot of nice structure, but we don't have a full classification of that. There are just way too many of those complex surfaces. But however, they're always algebraic though. Now, notice that when I say Cordeiro classification, it's not really for algebraic surfaces. It's in fact for complex surfaces. So there are differences here in the sense that if you have complex surfaces, complex space, meaning that the manifold locally is controlled by complex holomorphic functions. But you can be more restricted to those classes which are controlled by algebraic function, meaning polynomial. Okay? And so it's not a huge difference, but there are very non-trivial differences though. So there's an algebraic manifold. And then this is because things are controlled by polynomials, there are algebraic geometry, algebra play important role. There are lots of new other techniques that one can use to study that. So this is related to, you can use a lot of algebraic technique. It's very powerful technique. Yeah. So that's why Cordeiro's work is rather non-trivial, because there's not just for algebraic things, there's classification for complex surfaces. Okay. In dimension 3 or higher, mainly 3, if higher is much less, you only get a rough classifications, even in the algebraic case. For algebraic variety. Why not the complex manifold? Well, the first example we already do not know, which is a famous question. Many people claim that they solved the problem. Kind of example now is whether S6 has a complex structure. Okay, so in the complex case, this is widely open because in this first case we do not know already. So this is algebraic case. Okay, so if this is a complex case, which is completely unknown, and then one of the main questions is this Hopf conjecture. Question is whether S6 is a complex free manifold or not. Okay. But for algebraic variety, and it's the Morris minimal model program. MMP. Then I give you a way to classify them. But it's a rough classification, again, as I mentioned. Because, I mean, even in surface case, it's very detailed, but it's extremely complicated already. Now, again, in dimension bigger than 3, how do you do this thing? Okay, so you can first always look for the same questions, that what is the simplest one? How do you characterize the simplest space first? Like Poincare conjecture in the topological case, or whether the simplest S6 has a complex structure or not. But once in algebraic, then the first question you may want to ask, do we know which one is a CPN? Okay. How do you characterize CPN, for example? In all these questions, you always look at, can you first look at the simplest one? Do you know them? Okay. Characterization. Okay, and that is that two settings are basically the same. It's either called the Frankel conjecture, which is solved by Siu and Yao, or it's called the Hartshorne conjecture. Depends whether you say more in differential geometry language or you say more in algebraic language, Hartshorne conjecture, which is solved by Mori. Okay. So it says that if you start with a space M such that certain holomorphic bisectional curvature is positive, but just not loosely write this way, some holomorphic version of the curvature is positive, then it has to be CPN. So if you say algebraically, you mean the tangent bundle is ample. So these two are essentially the same notion. So there's huge, very subtle difference, but essentially the same. Okay, so that's so again, let me say the similar thing. The proof also is very similar to here. Wait, okay. So the proof. How do you prove something like this? How do you prove that something is CPN? Okay, CPN is like CN. Okay, what is CN? CN has a linear structure, meaning lots of lines, and the lines move around everywhere, all possible directions. Okay, if you know that, then you know it's a CPN. So you want to find a line which moves in a huge dimensional family, and that is CPN basically. Okay, it's passing through every point. Okay. So how do you find a line? Okay, in a line, or you can, in the case of a complex manifold, is a CP1, okay, inside. But it still have to be a line meaning very small degree, okay, with a control degree. But it has a huge deformation. Okay, and how to find them? Again, to find them is like finding a canonical metric here. The proof is to find enough line. Okay, so these are related to some CP1 inside of a small degree, but large family, that deform a lot. Okay. So that will characterize the space is the CPN. Okay. So there are two approaches. One is analysis approach, so the Siu and Yao approach. Or how to find them? Okay. They find minimum surfaces. So you can use minimum surface technique to find minimum surface. But then you want to do this. You have to move for a large family, but also small degree. How can you do that? Okay. So this is use a minimum surface technique. And then have a finite minimum surface, and use Boltzmann argument. Degenerately, minimum surface becomes singular. Okay, and then when it's singular, they continue to smooth it and then go on. So again, the point is that even though you try to find something smooth, you have to go through singularity. Okay? So singularity play an important role in all this classification question. So singular thing play an important role, but and then there's geometric analysis argument. And algebraic argument is by Mori program, Mori. So these are called bend and break. Argument. Again, you cannot find a line, but you can find some curve. There are lots of curves, right? Because the things are algebraically defined, so they can find lots of curves. Okay? But those are not the one that you want. And then you find some curve, whatever curve, and then you degenerate to something very singular, or you know that you can degenerate, and then if you hold some point fixed, and then you have to break out some other curve outside. Okay? Break out some other curve. And then eventually keep on breaking, and then once you break the curve the degree is smaller. So if you keep on breaking it, you make a very small degree. But how can you have so big a deformations? That has to use a characteristic P argument to find this. This is a characteristic P argument. I'm not going to explain this in detail, but just want to give you an impression that even whatever you're in topological setting, algebraic setting, geometric analysis, and they're all, even though the main purpose is to understand smooth object, singular object are inevitable. Okay? And the point about singular object is that when you don't know what happened, they are called singular objects. So it's extremely difficult to analyze. Okay. Yeah. Okay. So that is the lesson for today. All right. So that's just a quick introduction. So let's start with explaining our space. There's a menu. So that's the space that we're looking at. So let's move on. So if you think about at the beginning, how to study some geometry, well, you just look at some surface somewhere here. Okay? So the space is you look at a space in R3 or in Rn, whatever. So you just look at some Rn. In this case, I'm drawing R3 here. Okay. And there's some subspace inside. And how to get subspace? You have an equation constrain it. Okay. So maybe this is space, maybe inside here, maybe just divided by some equations. Maybe divided by smooth function, topological continuous function, algebraic function, something. Okay. And then you have to make sure that it's smooth. And you use implicit function theorem to argue it's smooth and so on. Okay. So that is extrinsic, meaning that you see the space inside a natural space that we know, flat space. Okay, so these are extrinsic geometry. But since Riemann, then we look at intrinsic geometry. That means that we don't need to use an ambient space. The geometry just should be just about this subspace here, not the ambient space. So intrinsically, so you get a space not inside bracket somewhere. Okay. And then the space meaning locally, we know is Rn. So locally, okay, is some open subset inside, for example, Rn, Cn, or doesn't really matter, depend on the setting. Some standard space. Okay. Inside of sitting is a big space. Each small piece is that. So maybe call this big N, okay? And this is small n. Okay? And then you put them together. And then you glue one pieces, and then you have another pieces, and so on. Just like you make your clothes, you have small pieces, various pieces, you put them together. Okay? And when you put them together, what you need is these grouting functions is the following. You need to avoid doing something terrible. So you have one piece. So this is a space. You try to make this space. Okay, so you have one pieces. This is U1. And then you glue another piece here. Maybe this one. Just like you do your small project or something. You pieces paper together. And then the thing that you really want is you do not want to have any bubble here. So this is bad thing. You want to avoid that. Okay? You want to make a very nice space. You don't want that in bubble. Okay? Okay, meaning the following. So this is something that you have to avoid. And that's the definition of a manifold. Okay? Or any other algebraic manifold. Okay? So from local pieces, and then you piece them together in a nice way. So avoid is the following. So what is the bad thing about this? Okay. So this thing is bad. So how to characterize the bad guy? Okay. So this is the two, when they piece together, you have something that you just supposed to identify, don't get identified. Okay. So these 2 points, you see that this point P and Q, they are supposed to glue them together. But all the nearby points are already glued. Okay? So this is bad because for any neighborhood, meaning that, so this is for any neighborhood, they intersect. Right? So you want to be good, meaning that you do not want that. Okay? You do not want this. Okay? So this space are called Hausdorff. Hausdorff space. Meaning that cannot happen. So meaning that for every 2 points, there exists a neighborhood, UP and UQ of those 2 points, and then the intersection is empty. And this cannot be done for these 2 points, because no matter how small the neighborhood is, they already get identified. So that cannot be true. Okay, so this is for any 2 points, you get disjoint neighborhood. Okay. So you want the space to be Hausdorff. Group with Hausdorff property. Now, this is how usually we talk about manifold. This is how we do. First of all, what is a neighborhood, right? So a neighborhood is some open set. So neighborhood meaning open set containing that. Open set containing the point. So what is a neighborhood? So a typical example is x squared plus y squared less than 1. So these are open sets in R2. Okay. Okay, so this is a neighborhood. You cannot do it if you are doing algebraic, because if you are a complex number or complexity, that doesn't make sense with less than 1. You can only say equal to something or not equal to something. Or only in the when the value is real, then you can talk about less than or equal to something. Okay. So closed set would be example would be x squared plus y squared plus 1. Okay. So the question is here, this is inequality, these are equality. This is a strict inequality, these are not strict inequality. Okay. So can you, not using this, what if you only use equal or not equal, then how do you characterize the Hausdorff property? Okay. The way to do it. So these are called usual topology or classical topology. I know classical is a good notion. Maybe usual is a much better notion. So here's another way to characterize these questions. It's called separable. So how do you avoid this? Okay, instead of using open set and of those type, another way is if you look at this sequence. Of course, all this point is the same as all that point because they're all grouped together. But they have different limit. This one has a limit here. This one has a limit there. Okay. So the statement is this is you want to avoid that. That is called separated. Separated. Is another way to describe Hausdorff-less. Is saying that every convergence sequence, so every sequence which has a limit should have a unit limit. Okay, so convergence sequence of points, meaning that it should have a limit. Just has the question is has a unit limit. Okay, so this cannot happen. Okay, that's why I can separate it. Okay, so this way the thing is now you do not need to use less than equal to. You can just use you can use only those open set which are like x squared plus y squared is not equal to something, for example, t or something. Okay, only need to use those. Okay. Then you can already, because these are just points, okay? Then you don't have to be in the whole neighborhood. Okay? So you only need such neighborhood. Okay? Meaning that you only use meaning that only topology. These are called Zariski topology. Only use open set. Is something like some functions is not equal to 0, something, things like that. Okay, a bunch of those. Okay, a union of those. Right. So these are called Zariski topology. So for example, what is an open set? Well, so this is a closed set. The whole complement is an open set. So all open sets are dense unless it's empty. Okay, but that is already enough to say points which are convergent. Okay. So if you are an algebraic geometer, then you usually use you have to use this because you do not have less than equal to notions. Okay. So say again the space or manifold, if you like. Okay, and it's defined in the following way that you have a piece. Locally, it's a standard piece. Let's just say Rn, or open subset, open domain Rn. Rn could be Cn or some other thing. So like that. Okay, and then you have to glue it nicely. So you have to no bubble. So this is either called Hausdorff or separated, one or the other, depending on the particular setting when you glue them together. So this is a gluing. That means that you identify this with that. Now the question is that you identify this open set, this is one open set inside Rn, to the other open set inside Rn, at least identify some part of it. Okay. And so they can be a continuous homomorphism or smooth diffeomorphism, biholomorphism, algebraically, and depend on the setting. So that gives you different type of manifold. So Gij, this gluing, if you require those to be continuous, and those are called topological manifold. If you have a smooth, then a smooth manifold or just manifold. Have to be smooth. It could be C1, C2, C1 alpha, anything, analytic, whatever you call it. Okay. It can be holomorphic, biholomorphism, holomorphic function, and that is called complex manifold. It can be polynomial, and they're called algebraic manifold. can be even more restrictive. You can be R phi. So these are all locally has lots of such function. But if you look at Rn to Rn, you can look at just R phi change of coordinate. So there's a much more restrictive. You get R phi manifold, projective manifold. You can same idea. Okay. Okay, now you have a space. Then what do you want to do with that? Well, do calculus. How about that? So calculus has two parts. One is differentiation. One is integration. Okay. And let's say just do differentiation today. So what do you differentiate? Well, that means that you have some quantity, something, and then you vary it. That's what differentiation. Well, when you say you want to measure something, how much it changed, meaning that you're measuring how much it changed compared to something that doesn't change. Okay. So how to differentiate a function? Well, let's say this is a function. This is a graph of a function. You want to differentiate df dx, right? Okay. Then this is not changing. And then you're comparing the thing which are changing compared to something that doesn't change, right? You have to compare. You have to have a background thing that doesn't change to say that how much the other one changed. Okay, so meaning that this one doesn't change. Okay, you're comparing to this. So this means that if you have this vector, if you keep on moving this vector, you have to fix what that means here. They are not changing, and then now you're comparing the other one to this particular one. Okay, so you have to compare. So to differentiate, you need to compare with something what we call a fixed thing. Okay? Fixed maybe a frame or something. Okay? To measure that the quantity of how much it changed. Okay? So how do you do that? Well, so let me draw that one here. So if you are in Rn, if your space is just Rn, okay, just R2, for example, okay, and you want to differentiate along a direction. So for example, you want to differentiate along a curve, along some curve here. Okay? You want to look at something, how much it varies along some direction. Because each time you differentiate along one direction. Okay? So let's say the direction along a particular curve. Okay? Then you have a notion that things does not change is because you have background fixed thing in Rn. That is the thing does not change. So what does it mean by having an Rn? Meaning if you have any vector in Rn, when you try to do it along the curve, this vector can just do the same thing. Right? The same vector in Rn. That's why when we learn a vector in linear algebra. So these are called parallel transport. You know, obviously, that's what they mean, parallel transport along gamma. Okay. Then if you have some other thing in here, then you just compare with this particular thing, basically. Any vector, you can do this parallel transport. So you can differentiate anything. So once you have this, then you can differentiate. T. So let's say the curve is parameterized by T, then you can, whatever quantity along the curve, then you differentiate that with respect to this fixed thing that does not change. Now, what if the space is not Rn? Okay. Then let's just try to do this extrinsically first. So let's say the space is not Rn, but let's say sit inside Rn. So you can have a bigger space to help you to fix the thing. Okay. Okay. So what you do here? So this is a big space, but the space that we look at is inside here. Yeah. Or maybe I should just draw. So this one's here. Okay. So this is the R2 inside, M2 inside R3. Okay. And if you're thinking about something on our end, then you can still keep on doing this parallel, just like this in our end. So that's what you do in our end. Okay. But now you're in M, so you only care about those vectors in M. Okay. Let me also draw one lower dimensional thing here. Okay. Let's just draw this as M. Okay. This is M in R2. This is M in R3. Okay. And if you do this, you only care about vector, tangent vector on M. Okay, so if you start with this tangent vector, if you try to do the transport, you only know how to do it in Rn. If you try to do it in Rn, once you do it, of course it's not along the tangent space anymore. Okay, and what do? Well, you project it back. Okay, so you move it a little bit, and that's not it's not a tangent vector, and then you project it back, and then you do this at each step. Okay, you keep on moving it using Rn to move it, and each tiny step you project it back. Tiny step project it back. Okay, the same thing here. So you do that, you have to first fix a curve along this one. Okay. So you choose a vector in M, tangent vector in M. You just differentiate things on M, but along the curve gamma, right? So that's why I have to do a two-dimensional example. Because gamma is just some curve inside M, because you differentiate along a particular direction. But the vector is in M, but not along M, gamma. So you do this, once you move a little bit, so you start with this one at the 0, you move a little bit, that might become outside. Okay, that's outside. And then you project it back to M. So you move it, translate, you get that one, and then you have to project it back to M. Okay, it keep on doing this process. Okay. Something. Okay. So these are called the parallel transport. Along gamma. Okay. Now, first of all, I have already used a particular notion called projected back, meaning orthogonal projection, meaning that I'm using an inner product. So I'm already using a metric. So otherwise, there's no way to. There's no other obvious way to consider you get a vector on the manifold. Okay, so you have to project it back. So because you need this notion, you have this nearby vector, you have to orthogonal project it back. So you need a metric. So how do you get a metric? So manifold have a metric. Well, because the space just sits inside Rn, and Rn has a standard metric. Basically, you're just using the metric on the big space. Because all the way we enjoy is just using the metric on the ambient space anyway. And so this one is really the ambient metric restrict to the subspace. Okay, we use that. I mean, that's what we enjoy. Yeah. But in fact, the projection uses the metric on the ambient space. But the main theorem is the following. So this is so once you have this, you know how to differentiate, right? As I just mentioned, because it is the thing that you doesn't move. Consider, and so you can use that as a background to compare things which move. And these are called the connections. These are called the reciprocal connections. Okay, you get to calculus. And the theorem or the proposition's main statement is, let's just draw this as gamma. Okay, standard pair of transport quantities. So these two are same notions, basically. Okay? One is differentiation, one is integrate. The theorem is given this. And then using this process, you get a connection, or the same as parallel transport on M. The statement is this depends only on G, but not on how it sits inside bigger space. Okay? Depends only on G. Okay? But definition is clearly depending on how it sits inside. Okay? So it means that this is intrinsic to G. So in fact, you can write it down completely in terms of G only. Okay? That is intrinsic. That's what I mean by intrinsic geometry. Why do I have to choose a curve one at a time? The reason is you cannot do it in all directions at the same time. That's not consistent. Okay? So this is the notion of curvature. Okay? So either you say in connection or say parallel transport. It's a more geometric say in parallel transport. So let me continue to say in parallel transport. So you start to have a M with a inner metric, and then this one you get a connection, or the same as parallel transport. Okay. Then what's the curvature? Is the following. So you have a space M. Okay. Pick a point on M. Okay. So if you go along one direction, you know how to do parallel transport. If you go another direction, you already know how to do parallel transport. The statement is that if you do this and then move that direction, or do it the other way, so you either do this one or that one, whether they are the same, even infinitesimally. Okay, and I tell you they are not the same. Okay, so let's just choose a basis here. So Tp of n, the tangent space, you choose a basis. I just write this way. Some tangent direction. I mean, so this is maybe EK, EL, and this is EK. So the n dimension, you choose two directions. That's what I mean. Okay, and then you do you do parallel transport along this. In fact, it doesn't really matter whether you don't need to use geodesic, any curve basically, because eventually you're doing things infinitesimally, so you don't really care whether the curve is geodesic or not. So just take any curve with this direction. Okay? You choose a local coordinate. You move this one, and then move that, and then move that to this one. Okay? And the difference will be, so you do the parallel transport. So let me draw the picture again. So you start with some vector, some other vector along the tangent direction, and then you move this. Okay, and then use this, and then when you get some vector. So you identify these two. Oh, you can use the other one. And then you get another vector. And then they are different. Okay? And then you measure the difference. Okay? So that infinitesimally. That means that you're choosing an epsilon times this, and then let epsilon go to 0. Okay? So differences. So maybe call the discrepancy or the error, whatever you call it, or parallel transport along boundary of a parallelogram. This is EK and EL direction inside M. Okay, you do this parallel transport on that. And the difference will be a map infinitesimally, okay? So infinitesimal error. Infinitesimal. And that quantity is called R, which depending on L and K, which is really a map from the tangent space of M back to itself. Okay? You start with this and then measure, come back. This is a linear map. Okay? You can write it as a matrix because you already choose a basis. So this you can write it as Rij KL. So this is a matrix for the fixed direction. So the curvature usually uses notation Lij, Lk. And that is called a Riemannian curvature. So that is Riemannian curvature. So it is this collection of information. Okay. And you can take the trace. It's called the Ritchie curvature, Ljk, which is a summation of Ijk. I. So these are called Riemannian curvature. These are called Ritchie curvature. And yeah. So for example, if you write metric, you choose the metric. Metric usually write summation jk dxj and so dxk and symmetrize it. The symmetric tensor, so sum of j and k. Okay, so this looks like this. This is also symmetric in j and k. So an actual question is whether they're the same, for example, or constant, and those has a lot of both geometric and physical importance. So a metric, so definitions, is called Einstein, with Einstein constant C. If the Ritchie curvature is the same as gjk at each point. Okay, up to some constant C. Some constants. It's called cohomological constant. Einstein constant. Okay. And then, as I mentioned, this was used a lot. For example, in the case of solving geometrization of free manifold, you want to try to find metric with constant curvature. That was the main purpose in that problem of classifying topological free manifold, is to find metric to solve that. And then in Frankel conjecture for characterizing CPN, then you have a holomorphic version of the Riemannian curvature, okay? And that you need that to be positive, okay? To find those line and then prove the manifold CPN, or in the algebraic setting, that positivity of the curvature is called the ampleness of the tangent. So why do I want to take these two, the trace of these two? Okay, why not? First of all, take IL or IK is no different because for parallelogram, these are skew symmetric. Because for example, K equal to L, of course that is 0, right? Because you're going back and coming back, of course it's 0. Okay, so there's a skew symmetric one. So therefore, summing IL and summing IK is the same up to its I anyway. So there's no difference. So the question is, why not setting I equal to J? Okay, that is 0 too. Okay, so that's why the only one is only summing I and L. Okay? Why I and J is 0? Because the connection we choose is that whenever you move it, it will project it. And that metric, that connection, that parallel transport preserves the metric. Okay, if you have something preserving the metric, then the determinant is 1 or minus 1. Okay, infinitesimally, trace is 0. If you look at a group which is determinant equal to 1, look at Lie algebra, then trace is 0. Okay? So that's why if you sum over I, J will be 0. Okay, that's the reason. Yeah. So if you own all the possible trace essential, this is the only one. Okay. Now, first of all, this one is only you have to do it on the manifold to look at these two, because if you can talk about connections similarly for other bundle, we are kind of mixing the background manifold and the tangent bundle to be this same space. You can look at the space M, but some other bundle do this parallel transport. So in that case, there's no way to sum over these two, because this is Ij is the bundle directions, LK is the manifold directions. You cannot sum over these two. But sometimes you can sum over that too, though. In what cases? Well, it depends what sum, though. Okay, so right here. So more generally, you can choose some other bundle over M. So in that case, we're using tangent bundle of M. But you can choose any other bundle. And then how to differentiate? Well, differentiation, as I said, is parallel transport, meaning a trivialization along any path. Okay? So parallel transport, or equivalently, what they call it connections, meaning that, the definition, is a trivialization of E along any path. Okay, so along any path, you are making the path cross out. Okay? And they have to be consistent in the sense that if you look at a path break into 2, 1, if you trivialize this part along this one, and then continue to do that, it's the same as you go from all the way. Okay? Because differentiation, you have to differentiate again. Okay? So it's just a compatible trivialization if you break the path. Okay? And that is connections. Because once you know how to trivialize it, then you know how to differentiate because you can compare it. Okay? Then they define the curvature exactly the same now. So you have an M. Okay. So at each point you have some space over each point X, and then you have some EX, some vector space Rn. Okay. And then if you move along a path, and then you trivialize that, so that becomes a product along a path. And then any vector here, vector here. So this is a connection. This is a choice. Okay. So in the Riemannian case that we just used earlier, we make the choice by using the metric. That where the choice is coming using the ambient space or orthogonal projection, things like that. So you make that specific choice. In general, you don't have that. But if you have a general manifold, that is a choice. You have a lot of such choices. Okay, that's a choice is a connection. And then curvature will be again the same. That now you have a point here. Let's say the tangent space as before. You choose a frame called E1 up to En. And then you also have, and then you move around small parallelogram, right? E, L, and UK. Basically, you just move around here and coming back. Okay, and then you see that the parallel transport upstairs, and then infinitesimally. And then now usually the curvature, the notation will be E. So that would be mapped from the EX back to EX. Because you look at a vector in EX, and then you go around the parallelogram, come back. And then that will become another vector, and then set epsilon go to 0. Something, okay? And so this depending on KL, okay? And again, this is skew symmetric in K and L, okay? But they may not be preserving, there's no metric anyway, because we are not making a choice of metric. So this is, you could possibly choose a trace, that is possible. There's also, so if you choose a metric, you choose a metric, or D, that means on each fiber you have inner product, okay? And then you also assume the connection preserve the metric, meaning parallel transport preserve the metric. Okay? Then this one will be skew symmetric. Then the trace on that part, this part will be 0. Okay? And again, as I said, you cannot trace this too. Let's say this will, if you choose the basis here, would be alpha beta. So this one may be out of call it F, S1 up to S R or something. Okay? There's no way to trace these two. They're just different spaces. Okay? But if you have no metric, you can take a trace. But if you have a metric and then connection preserve the metric, that trace is 0. However, you can choose Hermitian metric. That would be different. Though. That would be a different trace, though. So let me just write down the remark here. So the remark is that if this one has a metric, and assume that the parallel transport preserves the metric, another way of saying it, so you choose a connection, just right this way, a connection on this, and assume that it preserves the metric. Okay. Again, once you have a connection, you can differentiate. You say this is what preserved metric. This is the same as saying that if you have two vectors, the inner product is 0.2. You do parallel transport any path, then the inner product afterward is also 0.2. Okay, that's what we mean. And this is the infinitesimal way of saying it. Okay, so assume that. Then this one, if you take the trace along the E direction, meaning that you are looking at sum of F alpha LK. Okay, that would be 0. The same reason, right? Because preserving metric determinants, one trace is 0. However, so this is our M. M, let's say. Okay. However, let's say this is also complex. So this is a Cn, let's say. And then we choose so it's a complex vector bundle, meaning the Lewing function is complex linear. And then you also have a metric, and the metric is Hermitian. So this is a standard. So it's a Hermitian metric. And then you choose this one to preserve the complex structure and also preserve the Hermitian structure, and so on. These are E thing. Okay, this one has a complex structure. I mean, J squared is -1 fiber-wise, and then you have an inner product, and they are compatible. I mean Hermitian. Okay, Hermitian meaning that H E of that's not really E, J of something, or no J are the same. But that's what Hermitian means. Okay, so suppose you have a Hermitian thing and preserve that, then the trace is not 0, because you can do a different trace. Because the thing is, if you look at O2n, so these are infinitesimal preserve the inner product, and then if you choose inside also preserve the Hermitian metric, Un. Okay. Now this one could have a trace. This one is a different trace because this is a 2n by 2n matrix trace. This is a complex n by n matrix, and this one has a trace. Okay, this trace is in fact purely imaginary. Okay, so that if you look at the trace here, this is real trace. This will be 0, and then to this trace there will be an imaginary number, purely imaginary. Okay, and that is used quite often. Okay, that's why in the Conan manifold you can do this trace and do that trace, and the other trace they are equivalent. And that is a Canarian property. Okay, because otherwise you may be confused. Sometimes it looks like you are doing that trace because you are not using this one. You are viewing it as a complex n by n matrix. That has a trace. Okay. All right. Okay. So again, let me still talk about that, and then that gives you a connection, and people usually write that as a Levin-Civita connection. Okay. Okay. Let me say that again. So you have this space M intrinsically, and then you have this parallel transport. You fix a point. Background point. Let's just call it x0. Doesn't matter. Choose a point. And then you do this small parallel transport. They could be different. So you move by a small loop and come back. Or you take a parallelogram. It's the same because you can write down as many small parallelograms anyway. Okay? Take any contractible loop. Okay? not infinitesimal now. Okay, then you can go around, do the same thing exactly. Then that will give you a map inside O n. Okay, because the same reason. We are not taking infinitesimal now. This is honest path. Okay, take a honest path, and then you parallel transport along the path, depending on the path. Parallel transport along all the path, that will become a map from the tangent space to itself. Because the parallel transport preserves the metric. So therefore, when you come back, that map is orthogonal. Okay? Not infinitesimal because you're not taking any epsilon limit. So this is really a subspace in here. Okay? These are called so you look at all this that generate. This is called a holonomy group of the Riemannian curvature or metric. Depends. It doesn't matter. Okay? It's a smaller closed subgroup of ON containing all of this. Okay? Up to conjugacy, this is independent of the choice of the background point. Okay? Because you look at all possible contractible paths. Okay? So going from this one to starting from another one, they're conjugate to each other. Okay? And this is called a reduced holonomy group. Sometimes just called a holonomy group. Here are some examples. If the holonomy group G is SON, it's always in there. There's no assumption there. It's just it's inside SON. It's always true, as I just said so, because you always preserve that. But also we are looking at contractible loop, so they're always in the connected component. Okay, so that's automatically inside SON. Okay, it's in the connected component of ON. Okay, so it's always true. So this is just say that Riemannian manifolds. Okay, so it's not it's always true. So if the holonomy group is inside UN, meaning that now it's Rn is R2n now. Okay, it's a UN inside SO2n. Then such manifold is exactly the same as what we usually call a Kähler manifold. It's the same as a Kähler variant. Okay. If inside SUN, and those are called Calabi-Yau manifold. And if this is inside SPN, and that's exactly what it means by having Kähler manifold. So many of the space that we study geometry a lot, in fact, you can characterize in terms of this. Why is that true? Well, the statement is that if the holonomy group inside UN, what does that mean? Well, that means that at this point, you put a structure, like UN structure, meaning that the manifold, the vector space has a complex structure with a metric, right? Compatible metric. Okay. And then you use parallel transport to move that structure to any other point. But the holonomy inside SUN, that means that whatever you do, that structure is compatible. Okay? If you use parallel transport to move it around, it's independent of how you move that around. Okay? So that's why having this is just saying that whatever this structure at one point you can do the parallel transport to propagate to any other points. Okay? So therefore, classifying a holonomy group is really classifying what kind of geometric structure that you are imposing on the manifold. Okay? So therefore, it's important to classify them. So this really should be also put in the first hour. So this is classification questions. Classifications of Riemannian, meaning this, okay, mono Riemann reduced holonomic group. It turned out that there's a very complete classification by Berger. There are two types. The first one is like this. If it's not this, then the second one, the curvature is constant. These are very strong assumptions. The curvature is exactly covariantly constant. When you differentiate, you that is zero. Okay, like sphere, hyperbolic space form, and so on. Okay, so those are called locally symmetric space. And they are completely controlled by group data. So they are really some reductive group G over some subgroup, and then up to some lattice structure, okay, like Shimura variety. And what is the first class? Okay. The first class is to say that the manifold is defined over some norm division algebra. So norm division algebra, there are only 4 of them. Those are norm division algebra. But this way, the way of describing it is by myself and my former students. It's defined over a particular algebra and which is orientable or not. Okay, so oriented in the corresponding algebraic structure. Okay, so for example, this is a manifold defined over C, which is not necessarily orientable. When Calabi-Yau, this is defined over C, which is oriented. So meaning having a holomorphic volume form in this case. Okay, so in fact you can think about that all geometry, unless this is really like a model space, it's like so-called symmetric spaces. Otherwise, the geometry is really controlled by orientations and orientability and some algebraic structure by the norm division algebra. Okay. Right. So let me come back to ask the original questions that we have 2 ways of describing the space M. We start from an extrinsic way of thinking about naturally the space is sitting inside some Rn. And then later we say that, well, we just understand the geometry intrinsically without saying that inside. So we have this intrinsic space definition of M. Now the question is, given a space, does it prove it inside Rn? Okay, whether the intrinsic way of describing a space really gives you more manifold. Okay. You can ask the questions in different category. You can either ask whether this one, can you do this smoothly? Can you do it metrically? That means that the metric on M is really come from the global metric with stripped by M. Okay, isometric embedding questions. And you can also ask this question holomorphically. Okay. All right, so let me explain this. You can also look at R5 geometry, then you can ask similar question. This is called the developing map, so-called. All right. So let's look at this one. You can always do that. Okay? You may not be always do that, but you know, this question is very well understood in any case. So you always do that. Okay, that's always true. Why? Again, we are assuming that manifold is reasonable, like compact manifold, no boundary. You don't want to. I'm not assuming infinite topology or something huge. Okay, so any reasonable space. Okay, let's take a manifold M. How do you know that? What does it mean by the space inside Rn? You want to find that. You want to see what did you do. That means that you have to have a lot of functions that you want the following. Right? You want many functions. So each and many functions. Okay. If you have a lot of functions, you already get a map. Now the question is whether the map is an embedding. Okay. That means that such that you want to make sure that for every 2 points, okay, you can find 2 different functions, J in this class, or maybe some combination of those functions, such that they're different. So some coordinate is different, so it's embedding. Okay? But that is not enough, because you could have a circle mapped to R2, but the map could be like this. You could have a singular point here. It's not an embedding. Okay? It's still bijective in 2, but it's not an embedding. Okay? The reason it's not true is because this point sending to that point, but this tangent vector will go to 0 here. Okay? So it just says that you have 2 points which are infinitesimally close. You can think about this point and then the point plus the epsilon directions. And that 2 will both send to this one. Okay? So essentially it's the same question, basically. But just allowing the 2 points to be so-called infinitesimally closed. Okay, so essentially I just say this. I mean, the other is just minor differences. So for any 2 points which could be infinitesimally closed. So these are only, these are not for every distinct point, of course. But they allow it to be infinitesimally closed. Infinitesimally closed. Okay. So to make sure that this, you can think about this and this to the tangent vector. That will be there. And then that mode. Okay, so avoid that. So that cannot happen. So basically, you want to find enough functions to separate points, and so-called separate point and direction. That's what it means. All right, so how do you do that? Well, so you start with a manifold. Well, if you have a local chart, you know how to do it. Because if you only have one chart, that is an open subset in Rn, and then you just, those functions is enough. Okay? But these are not functions. These are not functions on M, though. Just like here is an example. So for example, this is M. Okay. And you have an open set like this. You identify with R. Could be, you could identify this with R, so that this one sent to minus infinity, that one sent to positive infinity, for example. Okay, so this open set, well, so you can separate this one. I mean, this is like R. But this function cannot extend to M. Right? So the functions, so you get some of these functions called f1 up to fn. But this functions is only defined on ui, though. Okay. And you want to find function on the whole space. This function is not defined on M. Okay. Well, what do you do? Well, that earlier problem was the only problem that is troubling. That means that you're going to, suddenly going to this point, going to this interval, then you send to minus infinity. Otherwise, if this one is not sent to minus infinity, let's say this one, this point, this is ui, this one sent to a particular point, like this, back to this interval. Then you can extend it everywhere, because you send to this, then you start it quickly, move a little bit, and then kind of stop there. The only problem is because this endpoint goes to infinity. That's why you cannot extend it. Okay, so all you need is these cutoff functions. All right, so therefore, if you have a function on here, you restrict to a slightly smaller one. Slightly smaller one. Maybe the original is bigger one. Okay, quite plus. Okay. If you originally have this function here, then you restrict to a smaller one that will not go to infinity in the boundary. Okay. And then you can restrict to the ui, the smaller one. Now this restricted function can be extended. This restricted function extends. But this is not compatible with this. Okay? And this is using a cutoff argument. I suppose most of you have seen it anyway. Okay? So that was the idea, basically. And so you have this. So you cover by a lot of this thing. And then you can use some number of functions to separate all the points inside U1 by first looking at charge which is U1 plus. Okay, and then do a cutoff. Okay. So you have enough function to cut off U1, and then you choose another open set, U2, and then you use another Rn to separate the point in R2. But then you can enough point to separate both U1 and U2 because you just cement to different space. You just get a bigger space anyway. And so if you cover the whole space by some finite number of ui, okay, then you get this map to this power finite. Embedded. Okay, so the idea, so the proof. So the proof is the following. So you want to write this as a finite cover of some chart, ui, and then each ui is an open domain inside Rn. And then this function, let's just call this fi. So fi is n different functions on ui. Okay. And shrink ui a little bit if needed. So I'm not saying writing all the detail. As usual, you have to make sure that we shrink a little bit, still a finite cover, and so on. So then just assume that it's a shrinker one. Okay. So, and then use cutoff. Okay, meaning that you don't shrink it, you use cutoff. Okay, it is the same statement. Okay. Then fi extend that extend fi to be an honest manifold map to this one. And that enough to, and this is a embedding not on F, it is embedding of UI. Okay? The other way I don't know. I mean, at least on the UI part, or this embedding by definition. Okay. And so therefore, if you look at M to just hold down all this, and you look at all the F1, F2. Okay, so this is sum Rn. Okay, it will be a global embedding. This is the end of the proof. And a quick remark. Can assume M, the embedding, you only need it to dimension 2n plus 1. Okay, so for example, if n equal to 1, then if you do this, then the embedding may be doing like this. If you move a little bit, it still looks like that. And you project it, still doesn't work anyway. Or the reason, but of course, a circle can embed inside R2s in some other way, but not in the original. But the thing is, if you do it in 2n plus, if you bigger it than 2n plus 1, then the following is in R3, you always have enough room, even though you intersect, they just move a little bit. Okay, so it's genetic assumptions. Okay, and let me skip that part. This is a standard embedding question. So that's if you can pick. So the idea is the proof is if you have this one to some very big Rn, if n is strictly bigger than 2n plus 1. Okay, then maybe you need to perturb a little bit or not. There exists projections. You just have enough directions so that call this F, call this G, G, such that G compose F. The compose with the projection is still an embedding. And then keep on doing it until you go to 2n plus 1. But once you go to R3, you may not be able to project it anymore, because when you project down, it may become an inverse curve. Okay? So that's a generic projection will work. It's just by counting dimension, basically. And the second is if you are giving a Riemann metric, whether you can assume that sit inside R bigger n, so that this metric is the restrictions. This is a lot harder question. These are called isometric embedding questions. And it's a PDE question eventually. And even the PDE method developed is very powerful and useful. So by John Nash, who proved that it's true. Okay? And but however, in this case, there's no good estimate of what the n is. There's some n. The third case, okay, if you have a complex manifold, you want to ask when you can find a holomorphic embedding inside Cn. Well, let's say, again, just like all the other cases, we are assuming that the manifold is compact, so there's finite topology and all this. So let's say compact complex manifold. So you need to find a lot of holomorphic functions. The first thing is there's no holomorphic function except constant. Okay? So this is never possible because there exists no non-constant holomorphic functions. Compact complex manifold except constant. This is a so-called maximum principal argument in harmonic function and so on from a basic complex analysis. It's a maximum principal complex analysis because the manifold is compact. If you have a holomorphic functions, then the norm will attain a maximum somewhere. Okay, and maximum principle says that cannot have an interior maximum unless it's constant. Okay? It's a harmonic function argument. Okay? So you can never do that. Okay. So Cn is not good, but you look at the thing which look like Cn too. But then you also want to be compact. The simplest one is Cpn. Okay. And this is solved by Cordeiro. So how do you do that? So you have to understand what does that mean. Previously, we mapped to that. You have a lot of holomorphic functions. You have something like a holomorphic function. Okay, what does that mean? Okay, so map, just not even holomorphic, just having a map to CPN. What does that mean? Okay, what does that? What does this mean? Okay, because there's no holomorphic functions. So what is CPN? CPN is all the lines in Cn plus 1. Okay. So what is line? Okay. So for example, you have C2. You know L2. It doesn't really matter. Okay. Line being the one-dimensional linear subspace passing through the origin. So this does not pass through the origin. Okay. So the collection of all this line. So why is this related to Cn? Well, you can put Cn inside. How do you put Cn inside? This is how Cn inside. You choose a directions. You write the Cn to be, so n is 2 in this example. You write n is n plus 1. Yeah. You choose a particular direction and then the rest. And then this one sits inside CPN because this is sitting inside here. This you just move that to one level. So this is a Cn plus 1. Let's see across here. Okay, let's already write this one. Cn plus 1, which is always Cn. Because every line will pass through the first floor once unless the line is on the 0th floor. Okay? So you see that tells us that what I just said is every line will exactly pass through the first floor once unless the line is in the 0th floor, which is a line in Cn. Okay? And so you can keep on decomposing and so on. Until the last one is this point. right, so let's take a look. Continue here. Take this picture. Okay. So, if you have a function coordinate of that, well, this one has a coordinate, right? This one mapped to Cn plus 1, identity map. Okay. So you write down the identity map as f0, call this 0, okay? f1 up to fn. Okay, so this is just z0, z1. These are just the coordinate function, right? This is exactly that. We just call it f, okay? Just because I want to find lots of functions, right? That's called f. It's just a really coordinate. Anyway, these are the things we want, right? But the thing is that this is not, that does not descend to the CPN. This is really a function on here only. But I want to say that this in some sense is a function. Well, in what sense is it a function? Well, let's say given some of this, let's say f1, let's say for example. So f1 is the coordinate, which is really secretly just z1, okay? So it's this function. Yeah. So that gives you a function on HL. So restrict to a line, Z1, this function Z1, is a linear map here. Each of them, any of that, basically, right? So in this sense, it's a function, right? So of course, I mean, you just, this is a function on Cn, of course, it's a function on L. So that's trivial. So what do I mean is the following. So you look at all this L. So this is CPN. So each element is what we call L. Okay? So this is set of all L. And then you put the L upstairs. So this is the copy of C abstractly, okay? Not canonically. This is a copy of C. And then you put all this together, they form a line bundle. I call it O minus 1. So what is a line bundle? Well, a line bundle meaning that a family of line, one dimensional space parameterized by base. That's what a line bundle is. Okay? So this is a line bundle. Over HL, they look at the L. Okay? Of course, you have another line bundle, which is a trivial line bundle. Trivial, completely trivial. This is just I call it O. Okay? Which is N. Sorry, this is N. Which is at HL, you just look at the same C. It's completely trivial here. So this is a non-trivial line because the line is moving, but this is a trivial line. What I just did is F1 is a map here, or any of such F. Okay? For each point here, you get a map from L to C. Is that clear? Okay. Another way of saying it, theory, you get a map from O to CPN. You don't do them for each thing in here, you get a map to the dual space. It's just a dual space. So this is just a joy or something, if you like. A map from V to U, the map, the dual is the U star to V star. But the dual of trivial is trivial. Okay? So the dual space is the same as O. This we usually have a notation called O1. That's a notation. Or O minus 1 is also a notation. So what it means is you get something from a trivial bundle to this bundle for each point. Another way of saying it is F1, you can think about it at each point is a section here. So this is this are called the sections of O1. And these are holomorphic, in fact. It's obviously holomorphic. You don't do anything non-holomorphic anywhere. Okay? So those are in fact also holomorphic sections. And that's a notation to that. That's usually called H0 or slot A1 CPN. Okay. So in fact, you have many of such C, this whole vector spaces here. So if you want to do it tautologically, this is an n-dimensional, n plus 1 dimensional space, we call it V, and this is the projectifications of V. And coordinate function on V is really an element in V star. It's a linear functional on V, so it's an element in V star. And each of this V star is naturally sit inside H0 of projectification of V of this bundle O1. And as a matter of fact, there's no more. This is exactly equal. Okay. And this gives you an explicit way of describing that. Meaning that these are not function on here. If it's function, then it will be trivial bundle. If it's trivial bundle, that means it functions. This is slightly twisted. So these are linear functions. So linear functions on V will be not a function, it's a section of O1. If you look at polynomial, meaning that if you look at homogeneous polynomial of degree D, okay, that would be this one, OD, meaning that the tensor power of O1 to the power of D. Okay? So if you are on Cn plus 1, these are all the functions on the vector space. Okay? They're of various degree. But they are not, the function does not descend to the projected space. They descend to be some twisted function in a way, meaning that section of different line bundle. And the degree of the polynomial is encoded in the how much twisted of the line bundle is. Okay? And well, this is good because this, you know, now exactly how do you compactify it? Okay. How do you get the map to CPN? So you start with a complex manifold. You don't have to be complex. I mean, anyway, some complex manifold, or just some manifold. I don't even have to be complex. Let's say, okay, some manifold. Anyway, I mean any M. Okay. If you have an M to CPN, okay, what does that mean? Well, this is, let's say you write as a projectification of some Cn plus 1. Okay. This space has a natural bundle called O1 line bundle, meaning that over each point L, you look at the same vector space L, well, that would be O minus 1, and that is a dual space. It's only like that. So it's called O1. Okay. And then the thing is, what is a line bundle? A line bundle means at each point you have a one-dimensional vector space very smoothly, and you can pull it back here. How? Well, if you have a point here, you want to attach to a line. Which one? Well, you look at the image, that has a line there. I just use that one. That's why I call it pull it back. Okay? So the line over the point is the same as the line over the image point. So that's a pullback. So you have a bunch of sections here. Well, if you compose, that will become a section here already. Okay. So here's the answer. Let me stop after writing down that the statement is the following. if you have a line bundle L, call this L. Okay. If you have a line bundle L, okay, and then you choose some sections S0, S1, up to Sn, for example. Okay. And then you're kind of thinking that this section really comes from here. Okay. Then you can map it to that. Then you can map this to Cpn by sending a point to. You write this as a Cn plus 1 minus the origins quotient by C star. Right? That is exactly all the line in Cn plus 1. And you send it to this point, S0x, S1x up to Snx. Only one thing you have to make sure that you avoid this one. You do not want to hit that one. So you need this one so that they cannot be simultaneous 0 at every x. Okay? So they have to generate L at every point. Well, what does generate means? It's a one-dimensional vector space. Okay? A lot of elements in a one-dimensional generate mean that it's not all 0. That is generate the one-dimensional vector space. Why do I want to do that? Because the same argument works for any vector bundle. You don't have to be line bundle. So that is a general statement to map to Grassmannian anyway. Okay? So that means that not simultaneous 0 in this case. Then you avoid this one. Then this is a well-defined map. Okay. And so let's just put it as an exercise. So basically, you just want to understand what I just said, then there's the finished exercise already. And furthermore, abstractly, if you look at V to be this vector space spanned by this, so this is n plus one dimensional space of all functions, and then this is canonically projectification of V star, right? Maybe call this V star as V then, one way or the other. Okay. And also, this line bundle L on M, call this map F then. It's the same as S, basically, but maybe call it S then. And then you have this line bundle O1, and this L is exactly pullback of O1. It's all tautological, basically. When you write down definition, they're all there. Okay, that's it. Okay, so say again, what do we have? So you have L over M. Okay. And then you choose some subspace of space of all sections. Okay. And then you have to choose that to be generating. So you choose a lot, then that will be generating because it's a continuous function, let's say. Generate the L. That's what it means. Okay? You choose a lot of sections, enough sections that so that at each point it's not simultaneous. So you can easily do that. Okay. Then you get a map from M to that. This will become defined Cpn plus 1. Well, maybe just there's some Cpn plus 1. Let's say. Okay. But you can keep on adding more sections. Maybe make a bigger space. Still generate. Then you put inside even bigger space. this may be a CPN plus 2 or something, or more section and so on. And this, in any of this, the O1 was pulled back to this map is called S. It doesn't matter which ON, it's always pulled back to that. Okay? And so on. You keep on adding a lot. In fact, you can basically, in some sense, take all of the section. Okay? The point is, this L will recover exact. So you have many possible S to recover the L, because any of such map gives you the pullback, will give you an L. But if you take the limit, that is independent. So let me write down what I just said. Statement here. If you look at all topological line bundle over M up to equivalences, meaning bundle, topological bundle isomorphism. So it's all line bundle basically, topologically. Okay. And then you choose a lot of sections. Then you get a map from P to CPN, where n getting bigger and bigger. The point is, if you allow n go to infinity, by choosing different sections, it's just eventually the map will be different, but will be unique up to homotopy. So this is a homotopy class of maps. From one space to another space. Okay? So this is this is a pi 0 of the space of all map from M to CP infinity. Measure CPN and go to infinity. That's what I mean. Well, and the map, and this is the bijections. It's not difficult to prove it, but yeah. That means that eventually these are exactly given by the homotopy class. Okay. And this space is in fact the second cohomology. I'm assuming the M is a very mild assumption. It's like finite CW complex or something. It's probably countable CW complex. This is H2 of M with integer coefficient. And under this bijection, if you start with a line bundle L, then the corresponding elements for the first Chern class of the line bundle L. So this statement just says that the first Chern class completely characterize the line bundle, and also every class is a first Chern class. Okay, so these are just using a smooth, continuous section and so on. I need holomorphic section later, which is much more difficult to come by. Okay, I want to get the map inside CPN for some finite number of n. Okay, and I also need the map to be holomorphic. Okay, I'll explain that next time. This idea of how to prove the Cordera embedding theorem. Yeah. Okay, that's yeah. The what? Yeah, what about principal bundle? What about G principal? Huh? Curvature. Yes. Yeah.
Do we have a geometric way?
Yeah, it's the same, basically. What is a principal bundle? Principal, okay, so the question was, what does it mean by connection and curvature on principal bundle? Okay. And if you have a vector bundle, okay, so each point, meaning that at each point you have a vector space. Abstractly, is isomorphic to a linear space, but we are not fixing identification. There's some identifications. So what can you do with a vector space? Well, having a vector space you can have a notion about vector. That means that you get a sections. But another notion about a vector space is you have a basis. Okay? So at each point, you have a vector space. If you do the same thing for each vector, that is called sections. Now, instead of doing that, at each point, you look at all the bases. Okay? We know that all the bases will be, if you're given any two bases, you can always move one to another by a unique element in GLR. Okay? So this one is not equal in the sense that this has a canonical element, which is identity. This one does not. It's only, and whenever you have two of them, the different is a unique element in GLR. These are called the torsor anyway. Yeah. And that is a principal GLR bundle. If you, instead of having a bundle, let's say the bundle also have some structure. It could be a inner product, complex structure, symplectic structure, some structure. Okay, you have a structure, and then you can look at all the corresponding bases. For example, inner product, you can look at a orthonormal basis, and then that would be OR, and then that would be principal OR bundle. And so therefore, having a connection here and having a connection here, what does it mean, a connection? It's the same as if it comes from a connection here. And they just write down what that definition should be, and that would be a definition of a principal G bundle. Yeah. And then that definition is you can do it without having coming from vector bundle. It's just when you try to find out what's the definition of connection curvature, you just think in this way, and then you find that abstractly, that notion. You don't have to become from a vector bundle. You can define abstractly. Yeah. So that. Right. If you want to recover, the way is if you have a principal bundle and then you look at the representations, so in this case, this is standard representation, then you can look at the associated bundle. So this represents called rho, pi, rho, G. G is OR in this case, on this rho over M. That will go back to the vector bundle. But the point is, in general, abstractly, you don't have a canonical representation. But any representation, you get a vector bundle. So if you have a principal bundle, doing this, you get a connection or a principal bundle, you get a connection on any associated vector bundle anyway. So this is a one way to just define the connection here, then you get the connection on all the possible associated bundle in a unified way.
Yeah. And what's the relation of the first class of the principal bundle and the joint bundle?
So it depends what you mean by first Chern class. So what do you mean by degree? So the statement is if you have a principal G bundle, okay, here's an equivalent definition. A principal G bundle is equivalent to be you have a space with a free actions by group. Then the quotient is called M, and then you get a principal G bundle, and then vice versa. Okay, it's the same statement basically, but the emphasis is different. This is free actions. All right. So have principal bundle, just like vector bundle, is a 1-1 corresponding to elements. Maybe call this, if you like Chern class, whatever class, some class. Is exactly a class by mapping from M to the classifying space BG. Topologically, all these are topological statements. Okay, BG. Okay. And what is characteristic class? By definition, anything about here, whatever coefficient you want, is called characteristic classes. Whatever is called here is called characteristic classes because it's just pulling back to M. That is a characteristic classes. By the construction, that is satisfied naturality. And by definition, there's nothing else that satisfies naturality except those things here. So this is all the possible. So these are by definitions, basically. There's nothing else that can have naturality. And these are all the things which can, because things are principal bundle of so-called representable. So these are all characteristic classes. And then you get associated bundle, you just keep on doing that. It's the same thing. Yeah, it's no different. Yeah.
So what's the relation of this CP with the
A joint bundle will be different bundle. Yeah, will not be the. So if you start with. So you're just asking the following questions. What is the relation for these representations and the adjoint representations? That's the only thing you are saying, right? Because you just do it as a family. That is the question about principal bundle, associated bundle. And this is just a Lie theory question. Yeah. So so this one, of course, this one. So you call this V, and this is just V tensor V star. That's the answer. Yeah. So for example, if you want to do C, if you want the first chain class, you need C. Yeah. So if you want to do C, then G, L, R, C. Okay, so the standard representation in this direction, okay, is V standard, which is the one on CR, okay, yeah, and the adjoint representations, call this G here. Adjoint representations, again, is V tensor V star. It's an endomorphism, right? So it's V tensor V star. In particular, first chain class of the corresponding vector bundle is always 0, because the first chain class minus first chain class. So if you look at E, it's a CR bundle over M, and then you get the associated, you do the principal bundle and the adjoint bundle, then you get exactly E star tensor E. The first chain class will be 0. This is standard representation. This is this one. If you ask the other, that's what I'm saying. Everything is just in the representation. There's nothing, all these statements, really nothing to do with the particular M. You're asking a representation question. You're just relating these two representations.
So it depends on the role you choose.
That's the point. The principal bundle, you just do it once, and then you get the corresponding, you get all the associated bundle data at the same time.
Why the holonomy fails to be
Well, because we're doing reduced holonomy. So in our case, we are doing the thing which are a contractible loop here. So in particular, there's no difference between you look at the manifold or its universal cover. Yeah. So otherwise, then if you look at bigger loop, then the holonomy would be maybe disconnected and all this other thing. Yeah. So we only look at connected loop. So these are reduced holonomy. You can look at the other case, but there are more detailed discussion about all the possible situations. Yeah. All right. So next time I'll explain the approach to do the quadratic embedding field. Yeah.